Hi everybody. I know it's been a while since I've seen you, so I wanted to refresh your memory on what we talked about with waves. So first of all, just the definition of a wave. It's a disturbance or movement that transfers energy through matter or space. So one important thing to remember here is that it transfers energy. There are types of waves that we talked about in class. One type is mechanical waves, and a subtype of that is transverse, where the medium moves back and forth at right angles to the direction the wave travels. For example, like in class, we talked about how if you're sitting in the ocean and a wave comes past you, say from the east, but you go up and down, that's a transverse wave. So that's moving in perpendicular to the movement that the direction that the wave is traveling. You can also have compressional waves where the matter moves back and forth. So if you're in the ocean and that wave comes in from the east, then you move toward the west and then back to the east. We laid the slinky out on the desk and we made a compression wave in the slinky. You can see there where the parts of the slinky get closer together and further apart. And sound waves are an example of compressional waves. Electromagnetic waves are also types of waves. They're made by vibrating electric charges. They can travel through space even without matter. That's how the light gets here from the sun, through radiation. Electromagnetic waves can travel through air and water also, but they don't have to have matter in order to travel. Here's the image we looked at in class. Take a look at how they're laid out with the gamma rays on one side, the radio waves on the other. This chart can be flip-flopped, so it doesn't matter which direction you show it. Notice that gamma rays have shorter wavelengths, so that means from crest to crest or trough to trough, that distance is smaller. They have a faster frequency, which means they're coming by this place much faster. And gamma rays have the highest energy. Moving on up, the radio waves are at the opposite end, so they have longer wavelengths. The distance from crest to crest or trough to trough is much longer. They have a longer frequency, or in other words, a lower frequency. They come by the point much less often, and they have the lowest energy. In the middle, we see the visible light, with ultraviolet, or with violet rather, being the shorter wavelengths of the visible, and red light being the longer wavelengths on the visible spectrum. Microwaves are those things we use to speed up the motion of the molecules in our food, to heat them up. You can kind of tell how long a microwave is, or how big a microwave is, because you know the little holes that you can see in the door. That's called a Faraday shield, and microwaves are bigger than that, so they can't get out through those little holes. Alright, so let's see what you remember. Gamma rays have the blank energy, the blank wavelength, and the blank frequency. They have the highest energy, the shortest wavelength, and the highest frequency. And on the opposite end, can you fill this out for radio waves? Do they have the most energy or the least? Longest or shortest wavelength? Highest or lowest frequency? Lowest energy, longest wavelength, lowest frequency. Characteristics. So here's some vocab that we did in class. The wavelength is that distance from one point on a wave and the next point just like it. So as I mentioned earlier, it could be from crest to crest, or trough to trough, or midpoint to midpoint. We measure that in meters. Frequency is the number of wavelengths that pass some point in a given time, and so that would be per second, because that's the unit of the hertz, is 1 wave per second. And then the speed, or v for velocity, is how fast that wave moves. So light moves at a constant speed. Sound waves move slower, like when you see a lightning bolt and then later you see or you hear the sound. And sound can change its speed based on what it's traveling through. So it moves slower in water than in air, and it moves faster in warm air and slower in cold air. So here's an image of those characteristics. The entire height is from crest to trough. Amplitude is from resting point to the crest. Wavelength is from crest to crest, or it could be from trough to trough. That would be the same distance. And if we're looking at a compressional wave, it does not have crests and troughs, but it does have places where it's the wave is scrunched up. So like the slinky, the bands of the slinky are scrunched or stretched out. So where they're scrunched together, that's a compression, and where it's stretched out, it's called a rarefaction. So the wavelength would be from like point to like point, so from compression to compression, or from rarefaction to rarefaction. All right, so now for the math. The speed of waves is calculated by multiplying its frequency times its wavelength. So speed in meters per second, frequency in wavelengths per second, and wavelength in meters. We have the triangle that you can use for a tool. Here's the formula. So if you want to find the speed and you have the frequency and the wavelength, you just multiply them together. Let's say you have the wavelength, then you'll need to divide the speed by the frequency. Or vice versa, if you're looking for frequency, you would need to divide the speed by the wavelength. So let's practice. All right, what is the speed of a sound wave that has a wavelength of 2 meters and a frequency of 170.5 hertz? As usual, we want to figure out what we know and then figure out what we're looking for. So here what we know is the wavelength and the frequency, and we're trying to find speed. So using our formula, we fill in what we know. We're looking for speed. Here's what we know: the wavelength and the frequency. So all we have to do is multiply these two together to get 341 meters per second. All right, a wave traveling in water has a frequency of 500 hertz and a wavelength of 3 meters. What is the speed of the wave? Again, find out what we know and what we're looking for and set up our equation. If we know the frequency and the wavelength, so we know frequency and wavelength. If we fill those into the triangle, we've got the frequency of 500 hertz, the wavelength of 3 meters. We're looking for the speed or the velocity. So what are we going to do to those two numbers? You got it. Multiply. My dog is barking at the wind. Okay, so don't forget, sometimes you're looking for wavelength or for frequency and you already have the speed. So you will have to divide instead of multiply. So here's our formula. Here's our triangle tool. Here's our problem. The lowest pitch sounds humans can hear have a frequency of 20 hertz. What is the wavelength of these sound waves if their wave speed is 340 meters per second? So let's think about what we know. I know the speed and the frequency, and I'll be looking for wavelength. Don't forget, sometimes you're looking for wavelength or frequency and you already have the speed, so you'll have to divide instead of multiply. Alright, so here's our problem. The lowest pitch sounds humans can hear have a frequency of 20 hertz. What is the wavelength of these sound waves if their wave speed is 340 meters per second? So this time I know the speed and the frequency, and I'll be looking for wavelength. So using the triangle, I fill in what I know, but this time I have to divide. So if I have 340 meters per second, that's the velocity. The frequency is in the lower left, so this is going to be setting up the numerator and the denominator. I'll be looking for wavelength, so this time I have to divide 340 by 20 to get 17 meters as my wavelength. Alright, one more problem. The highest pitched sound humans can hear have a wavelength of 0.07017 meters in the air. What is the frequency of these sound waves if their speed is 340 meters per second? What do we know? We know the speed, and we know the wavelength this time. So we know the velocity and the wavelength. We'll be looking for frequency. So if I fill in my triangle tool, I have the speed and the wavelength, and I'm looking for frequency. So I will take 340, divide that by 0.017 to get the frequency is 20,000 hertz. Okay, I think you're ready to give those practice problems a try, and please let me know if you have any questions.